suppose we had a tensor S mu nu, which I'm going to write as a table of numbers. Doesn't mean you should think of it as a matrix. It's just a nice way of quickly telling you what it is. So I'm going to be in coordinates x, y. That says squared. And I'm going to change to coordinates x prime is 2x over y, and y prime is y over 2. So I want to get S mu prime nu prime. So I'm going to write it out. The only way the notation allows me is with an upper mu, lower mu prime, upper nu, lower nu prime. And so you can see I'm going to need derivatives of the old coordinates with respect to the new ones. Now, I can't just straightforwardly immediately get them because I actually have the new ones in terms of the old ones here. So the first thing I'm going to have to do to start getting dx mu prime is invert these. So let's see if I can manage to invert. So I see y prime is y over 2. So here's a y over 2. So it looks to me like this top equation becomes x prime y prime equals, x. Stop me if I'm wrong. I bring the 2 over y to the other side. It becomes y over 2. And this equation I can write as y equals 2y prime. So I managed to invert. Now I have x equals something and y equals something. And now I can get my Jacobian matrix. So let's just write them all out. Let's write out dx. Thank you. So let's just write out. We need d unprimed d prime. So let's just do them all. dx prime, looking up here, is y prime. Do stop me if I make a mistake. dx dy prime is equal to x prime, according to the equation up here. Maybe I should organize them the way the Jacobian is usually organized. So this one will go here. And then we'll have dy dx prime. That's 0. Y is just equal to y prime. And we'll have dy prime equals 2. Okay, and now I have to write out all these terms. So let's start with S mu prime nu prime equals 0 prime. Oh, this is spatial, not 0. Equals S, let's call it x prime, x prime. So there's going to be a bunch of terms. There's going to be sxx, dx, dx prime, plus sxy. Oh, I left out a term. I forgot could square it, but I'm just going to be very explicit today. Dx prime plus sxy, dx prime, y, dx prime plus syx, dy, dx prime plus sy. I always forget the second one. And so you can tell how much actual calculation I do. This is lowered x, so this needs to be x. And everything in the bottom is x prime, because that's our lowered index. And then finally, syy will be dy dx prime, dy dx prime. And we just keep going. So we look up sxx. That is 1. Dx prime was y prime, so that's y prime squared. Do tell me if I make a mistake. Sxy, was 0, so that's easy. Same with syx. Syy is x squared. And we need dy dx prime, which is 0. OK, so this one came out to y prime squared. OK, and that's how it goes. And you just do the other ones. You do x prime, y prime equals all that, and sy prime x prime equals all that, and sy prime y prime equals a similar expression. And I seem to have written the answer in my notes. But one thing I want to show you after showing you this kind of annoying way to do it, where you write out all these different terms, is a slick notation you can use to do these calculations that will save you a lot of effort. Now, if the notation doesn't help you, by all means, do it the long way. But let me show you one of the ways in which this notation that we're introducing works in your favor. Show you why I insisted that the dual vectors are gradients of coordinates. Well, that's a great notation, because look what I can do. I can write the abstract tensor S as S mu nu dx mu dx nu. Now, there was a tensor product in here. I'm not writing it. Right, so the idea was this is a 0-2 tensor. Its basis is formed from tensor products of one forms. And so this is the abstract equation for it. And now I can write it out. So remember what S was. I'll just put it on the board again. It was 1, 0, 0 x squared. So I can just write out, this is d, so this is the, right, this was the x column, this is the y column, x, y. So I can just write this, well, it was 1 times dx times dx. So it's just dx squared. There are no cross terms, so 0 times dx dy plus 0 times dy dx plus x squared dy squared. Okay, so this is another notation for that tensor. Okay? And actually, when we get to the metric, we always write it this way, because it looks like it's a traditional thing. It looks like lengths of little triangles of sides dx. Why is this good? Well, in the other notation, we just got one component. We wrote out all those terms, and we just got one component. In this notation, we can do everything at once. So also remember, we had x. We had inverted. You don't have to invert in this version. What am I doing? So let me write down the coordinates again, the coordinate transformation again. So we had x equals x prime, y prime, and y equals 2y prime, according to my notes. So now we just use our calculus stuff. We say, well, dx. We all know how to do that, right? We learned that in high school. It'll be dx prime times y prime plus the other term, x prime times dy prime. And what's dy? That's just 2 dy prime. So then I just plug these in. So I just write dx squared is y prime dx prime plus x prime dy prime squared plus, now what's x? Well, that's x prime y prime squared. And what's dy? Well, that was 2 dy prime, so 2 dy prime squared. Now I just simplify. Now I just multiply things out. So I get y prime squared dx prime squared plus y prime x prime dx prime dy prime. Now the tensor product doesn't commute. So I do have, there is secretly a little tensor product there. So I do have to do yx and xy separately. Let me move some stuff out of the way here so we have more room for our calculation. Okay, we're just simplifying now. So now we also have the term y prime x prime dy prime dx prime, and we have the term x prime squared dy prime squared.
So when you say the tensor product is a q, you're referring to not switching the order of
The d's.
differentials?
That's right.
X's
The x's and y's are just the coordinates on the manifold. Those are numbers. But these dx's are basis 1 forms being tensored together. So that was the first term. And then I also have, from the second term, 4 x prime squared y prime squared dy prime squared. So now I can collect everything together. So let's look at the dx prime squared terms. I see one here. I don't have any others, so it's just y prime squared. And then we have y. Yeah, I guess I'm really just copying most of the first expression. Y prime x prime dy prime dx prime plus, and it's just the last two terms that are the same. So let's write dy prime squared x prime squared plus 4 x prime squared y prime squared. Is indeed what I got. And now if we want, we can translate this back into a matrix. We just read the components off. So what we have now is S mu prime nu prime is the matrix. And we just look, OK, our coordinate basis here in the x prime coordinate basis is appearing here. So I need to put y prime squared in that component. Here is x, y. So row x, column y, that's y prime x prime. Yx is also y prime x prime. And the dy squared is x prime squared 1 plus 4y prime squared. Let's make that readable. So x prime squared plus 4x prime squared y prime squared. OK, so both of those were a little annoying. They had a few lines. But in this one, I got all 4 components of the tensor in one fell swoop, whereas up here, I only got the, and this is just a 2 by 2. So here I just got the x prime component, which was y prime squared, and there was still work to be done to get the others. But when we did it all with the nice differential notation, we got the y prime squared in the x prime spot, and we got all the other ones too. So generally speaking, the most common tensor you're going to transform is the metric tensor, which we'll talk about next time, maybe a little bit today, which has 2 downstairs indices just like this and is actually symmetric just like this. And you will, want to do the transformation this way to save yourself some calculation. OK, so I know this stuff is boring, but at least we've done one example in class of how to actually do these calculations. Yeah? I can try.
Yeah. So how were we able to write this expression for S?
This?
We derived it somewhere, or we just said that?
Well, let's go back to where we said it and then decide if it was a derivation or an assertion. So the claim is that we did define vectors, and I referenced some arguments but didn't give them for why that really gives you an n-dimensional vector space at each point on the manifold. And then I said, once you have that, we can get tensors in exactly the same way we did in special relativity. And the idea was you started with your basis, d by dx mu, it's now called, for vectors. You got a natural basis dx mu in one forms by this rule up here, by this rule. And then you got a natural basis for any tensor by just tensor producting these together. And so that equation for S that I wrote as S equals its components times dx alpha dx beta is just this equation here.
You didn't have any partial derivatives.
No, because it had two downstairs indices. So the partial derivatives are the coordinate basis elements for vectors, which have upstairs indices. S mu nu, the example, had only downstairs indices, so you use the dx's, which are the coordinate basis elements for one forms, aka downstairs indices.